if we integrate this rate law, we can get the integrated form. We won't go through the details of doing this integral, but the final answer you get is that the concentration of A is equal to concentration of A naught minus concentration of A at equilibrium. I should say that the limits on our integral is that at t equals 0, the concentration of A is equal to concentration of A naught, and at t equals infinity, if we give it enough time for the reaction to proceed to completion, then this goes to the value of A at equilibrium, right? Give it enough time to react, it reaches equilibrium. Okay, so we have this difference between these two, and it's an exponential here, e to the minus k1 plus k minus 1 times t, sort of our combined rate constant there, plus concentration of A at equilibrium. Now, one other thing we can do with this is if we rearrange this and take the natural log, we can get a slightly different version of this equation where we have the natural log of A minus minus A at equilibrium is equal to the natural log of, sorry about that, that should be parentheses, A naught minus A at equilibrium minus k1 plus k minus 1 times time. And so we can go ahead and this is an equation of the form that where we have, this is our y, this is our b, so this is just a constant here, and then we have our mx, right? So we'll have y equals mx plus b, and we can, if we make a plot of the natural log of the difference between A and the equilibrium value of A versus time, that will let us find the value of k1 and k minus 1, right? Our slope is equal to minus k1 plus k minus 1. So that's one way of getting the combination of k1 and k minus 1. Now, of course, we usually want to know these separately, so there's one additional piece of information that we would need to know to be able to separate these out. We need to know these independent of each other. And the key here is that at equilibrium, we know that this derivative goes to 0. So this is specifically at equilibrium. This equals 0. And we wrote out an expression for this before where we had k1 times A equilibrium minus k minus 1 times B at equilibrium, right? So at equilibrium, these concentrations are specifically the equilibrium concentrations. And so we can rearrange this equation and say that, okay, well, k1 times A at equilibrium is equal to k minus 1 times B at equilibrium, right? These rates are equal to each other at equilibrium. And we can rearrange this equation to say, okay, that gives us k1 over k minus 1 is equal to concentration of B at equilibrium divided by concentration of A at equilibrium. But what we have on the right-hand side of the equation here is simply the equilibrium constant. So this is equal to the equilibrium constant. And so now we have a relationship where if we know the equilibrium constant for the reaction, we can then figure out what are the specific values of k1 and k minus 1. So these three values are directly related to each other. Now this is specifically for a first order reaction in either direction, but the basic idea is similar for other reversible reactions. One last thing I wanted to show before we end this video is what the time dependence sort of looks like. This is for a generic reaction here. We're plotting either A or B on the y-axis, and so specifically this curve up here. Let me get a better color here. The curve on top here, this is the A curve. So this is plotting concentration of A divided by A naught. So at this point, at the beginning of the reaction, we have all A, right? And the value is equal to A naught. And the curve on the bottom here, the dash curve here, this is the B curve. So this is the concentration of B over B naught. And so we start with none of that at the beginning of the reaction. And as the reaction proceeds, depending on the specific rates, we see a decrease in A and an increase in B, as we'd expect, and they approach a steady state as we approach longer and longer times. And so on the right here is where we have equilibrium. right, as we give it enough time for the reaction to proceed to completion, it reaches equilibrium. And the specific values here depend on the rate constants for our reactions. So this is a plot from your textbook with some specific values of the rate constants. Let me just write those down so you have them. So the rate constant is K1 is equal to 2.25 times 10 to the minus 2 per second. And K minus 1 is equal to 1.5 times 10 to the minus 2 per second. Okay, and so we can see that, because K1 is larger than K minus 1, we overall end up with more B than we do A when we reach equilibrium. And we can also see that the ratio between these is just going to be equal to Kc, as we mentioned above. And so we should end up with more B than A at equilibrium. So just a visual representation of sort of the process that we're looking at here. So that's it for reversible reactions. In the next video, we'll look at the temperature dependence of rate constants in the Arrhenius equation.